In this video, we're going to look at another application of work integrals. A cable with linear density of 3 kilograms per meter is attached to a large container filled with diamonds that has a mass of 500 kilograms. The container is initially at the bottom of an 8-meter deep vertical mineshaft. The container is lifted up to the midpoint of the mineshaft by winding the top half 400 meters of the cable. Find the total work required in joules. So we have gravity, that's 9.8 meter per second squared. We have the density of the cable, linear density, which is 3 kilograms per meter. There are three components here, three components of the total work. Then we have to add them all up. So the first component is find the work required to lift the container of diamonds 400 meters to the halfway point. The second component of the work is find the work done to lift the top half of the cable, the top 400 meters. And the third component is find the work done to lift the bottom half of the cable. All right, so here we have some drawings here. We have the container of diamond at the bottom of the mine shaft. This has to be lifted up 800 meters. Now, we also have the top half of the cable that has to be lifted piece by piece to the top. And we have the bottom half of the cable that has to be lifted as a whole unit. And those have to be treated separately. And we're going to talk a lot about that. So we have a drawing here. We have a segment of the rope. And you can see that when this segment of the rope is y units from the ground, it has to be lifted 800 minus y units to reach the halfway point. So we have the cable linear density, that's 3 kilograms per meter. That means every meter of this cable has a mass of 3 kilograms. We have gravity on Earth, that's 9.8 meter per second squared. And we have the mass of the container of diamonds, which is 500 kilograms. All right, let's find the work for the container. The work for the container, the mass is 500 kilograms. Mass of the container of diamonds. Force is mass times gravity. That's 500 kilograms times gravity, which is 9.8 meter per second squared. And if we put this into the calculator, we get 500 times 9.8. This is 4,900 newtons. And we have the work. Work is equal to force times distance. So we get 500 times 9.8. times 400, and this gives us 1961234. So that's how many joules of work is required to lift the whole container of diamonds 400 meters. Why 400 meters? Is because we're lifting it up to the halfway point. The whole distance is 800 meters. Half of 800 is 400. That was pretty easy. Now, certainly we can use an integral to do the same job. So the work would be integral from 0 to 400, 500 times 9.8 times dy. But the point is, an integral was not required. We could just use force times distance. That's not the case for the second part, which is the top half, the work required for the top half of the cable. We need an integral to solve this. So that's a key distinction, is sometimes you can just use work is force times distance, and sometimes you have to use an integral, and we'll talk about the difference between the two. So now let's look at the work for the top half of the cable. A piece of cable of length dy at height y meters from the bottom of the mine shaft has a mass of 3 times dy. So differential mass is 3 kilograms per meter times dy. dy, the units of dy is in meters, of course. This gives us the mass of a small segment of cable. Now, the force of gravity acting on this piece of cable would be 3 times 9.8 times dy. All right. So differential force, dF, is equal to 3 times 9.8 times dy. dW is going to be 800 minus y is equal to 800 minus y times dF. Why is it 800 minus y? Let's talk about that. So 800 minus y, if you look at a diagram, when this segment of rope is y units from the bottom, that segment has to be lifted 800 minus y units to reach the top, because the whole distance is 800 meters. So that's very important, this 800 minus 1. All right, so dw is equal to 3 times 9.8 times 800 minus y dy. So essentially, mass times gravity, force times distance. This part is a distance, this part is a distance, and 3 dy, this part is a mass, right? That's the mass, and then gravity is 9.8. All right, so this is the work required to lift a small piece of the top half of the cable, 800 minus y meters. So what are the limits of integration? The limits of integration, they're not 0 to 400, no, because we're lifting the top half of the cable. So we go from y equals 400 as a lower limit of integration, and the upper limit of integration is y equals 800. dw. Substitute dw in, we get 400 to 800. 3 times 9.8 times 800 minus y dy. So now let's find the total work required to lift the top half of the cable. Constants pass right through the integral, so work is 3 times 9.8. Integral from 400 to 800. These are y limits. 800 minus y dy. And 3 times 9.8, that gives us 29.4. And integrating 800, finding the antiderivative, that's going to give us 800y. Applying reverse of the power rule, what's the integral of y? That's y squared over 2. Add 1 to the exponent, divide by the same. Evaluate it from y equals 400, lower limit, lower y limit, and upper y limit, 800. Y equals 800. Now apply fundamental theorem of calculus, and we can solve this. So we get work is equal to 29.4 times 800y minus y squared divided by 2. Evaluated from 400 to 800, applying fundamental theorem of calculus. Work is equal to 29.4. Putting the upper limit in, we get 800 squared minus 800 squared divided by 2. Now put a lower limit, applying fundamental theorem of calculus. 800 times 400 minus 400 squared divided by 2. Close off the brackets. And if we put this into a calculator, we're going to get work is equal to 2352,123 joules. So this is the work required to lift the top half of the cable. All right, so now it's really important to realize that the top half of the cable and the bottom half of the cable have to be treated separately. Let me see if we can draw a diagram here to illustrate this. So here's the full distance, 800 meters. And here's the mass at the bottom. Now, when it reaches the halfway point, it's going to look like this. So you can see how the top half of the cable was lifted 400 meters. But the bottom half of the cable, it basically just moves up as a whole unit. That's the reason. So we're going to talk about that. Let's look at the work for the bottom half of the cable. The key concept is the top half of cable and bottom half of cable have to be treated separately. The reason for this is the top half of the cable has to be lifted piece by piece to reach the top. But the lower half of the cable is lifted as a whole unit, 400 meters of cable, to reach the halfway point. So for the lower half, we don't really need an integral. Of course, we can use a definite integral if we want to, but we don't need it. That's the point. So if we apply a formula, it's going to be work is force times distance. 400 meters of cable times linear density of 3 kilograms per meter gives us the mass of the 400 meters of the cable that has to be lifted 400 meters. And gravity is 9.8. Multiply these numbers, force times distance, and we get 4704 with 3 zeros joules. So now let's set up a definite integral and see if we get the same answer. So work is equal to integral from 0 to 400, 400 times 3 times 9.8 dy. This part is the mass of the 400 meters of cable. This is gravity, that's g, and dy is the distance. So work is equal to 400 times 3 times 9.8. Multiply these numbers out, we get 11760 integral dy. Y goes from 0 to y equals 400. So we're going to get 11760 integral of 1 dy is just y, evaluated from 0 to 400. So the result is going to be work is equal to 11760 times 400 minus 0. This gives us 4704.123 joules. This is the same answer as using the formula work is force times distance. Work is force times distance. That gives us mass times gravity times distance. So work is equal to 400 meters, that's 400 meters of cable, times linear density 3 kilograms per meter, times gravity 9.8 meter per second squared, times the distance that the 400 meters of cable has to travel to reach the halfway point. So 400 meters. If you multiply all of these out, you get 4704.123 joules. You get exactly the same answer as when we applied an integral. So an integral was not really required. But it was required when we found the work done to lift the top half of the cable. And we're going to talk about why that is. All right, so now let's look at the different components of the work in terms of an integral. The work for the container, that's equal to integral from 0 to 400, 500 kilograms times gravity 9.8 dy, and this gives us 1961234 dy. We also found it by going work is force times distance, so 500 times 9.8 times distance of 400, and we got the same answer. So we didn't need to integrate. Sorry, let me fix this. This should be joules, not dy, joules. Now let's find the work for the top half. The work for the top half in terms of an integral is the integral from 400 to 800, 3 times 9.8 times 800 minus y dy. And it's precisely because we had a function of y here that we had to use an integral. We need an integral in this case. So this came out to be 2352.123 joules. Now work for the bottom half. The work for the bottom half is integral from 0 to 400, 400 times 3 times 9.8. So this part is the mass of the 400 meters of cable. This part is gravity and times dy. And we also could certainly find the work for the bottom half of the cable without using an integral. So when we applied an integral, we got 4704.123 joules. Now we can just go 400 times 3 times 9.8 times 400. This part is the mass of the 400 meters of cable, gravity times distance. And we get exactly the same answer. So why is it that we need an integral for the top half of the cable and we don't need an integral for the bottom half? The reason is this piece. This 800 minus y is a function of y. We don't have anything like that for the bottom half. This is all constants. You see, that's the main difference. So when you add all of these up, the total work done, which is the work for the container, work for the bottom half of the cable, and work for the top half of the cable to reach the halfway point, the total work done will be 9016.123 joules. That's a little bit more than 9 million joules. That's a lot of work. All right, thanks.